Then speaking of the questions, you're welcome to ask questions during the talk. To do so, you can either use the raise the hand option of the Zoom or use the chat to send a private message to me and the speaker. And then I'll let you ask a question during the talk. And then if there's any problem or concern you see, then please let me know using the chat again. And then next, yep, I think this is pretty much it for the announcement. So now we can start the talk. So today we have Ryoma from Akita University in Japan, and he'll talk about asymptotic approximation by regular languages. So Ryoma, please start.
Okay, thank you for the introduction. Okay, I will share my desktop. Okay. Okay, so thank you, Koko-san, and hi, this is Ryoma from Akita University, and I want to say thank you for the organizers who are inviting me. I'm a bit sleepy actually because in Japan now is 11 p.m. so the outside is completely dark. Maybe owl is flying outside, but I'm still happy because I'm really appreciated to have this opportunity. Thank you. So today I would talk about my recent work, and this talk is basically based on this paper, which will be appeared to SOFSEM, this next year's SOFSEM. And the draft version is available at my webpage, so please see my paper if you are interested in my talk. Okay. So basically, this talk consists of 5 parts, and let me first explain the motivation of this work. Okay, the motivation of this work is originally came from the long-standing, well-known open problem, which I call the primitive words conjecture, which originally posed by Domoshi, Horvath, Ito in their 1991 paper. And first, I explain what the primitive word is. So primitive word is a non-empty word W, such that it cannot be represented as a power of any shorter words. Okay. And we denote by QA the set of all primitive words over A. So hereafter, we only consider the case the alphabet consists of 2 letters A and B, and we simply write Q. Okay. So here is some example of primitive words. ABA is not a power of any shorter words, so it is primitive. So it is in Q. But if we add letter B at the end, we obtain AB, which is a cube of a word AB. So it is not primitive, okay? And the open problem asks about context freeness of this language Q. And actually they conjectured that Q is not context free, okay? And yes, I believe this is not context free, but still this problem is unsolved, okay? So here I want to give some basic property of primitive words. So primitive words is like prime numbers in numbers, because it gives us a unique good factorization of word, non-empty word. I mean, for every non-empty word W, there exists a unique primitive word that W can be represented as the power of its primitive words. Okay. And here is another characterization of primitivity by using the notion of conjugation. And for a word W of the form UV, we denote its conjugate by U inverse WU, which means the remove prefix U and add U as a suffix, and then obtain VU as a conjugate of W by U, okay? And if U and V are non-empty, then this conjugate is called a proper conjugate. So this fact gives another characterization of primitivity, and it is sometimes called the Lindon-Schutzenbeger theorem. Namely, W is primitive if and only if W is not equal to every proper conjugate. Okay, so if we think about a conjugation as a partial morphisms on words, so primitivity has the same flavor with rigidity in model theory. Okay, and yes, so primitive words gives us a very good factorization of words. So it plays a central role in algebraic coding theory and combinatorics on words as well. Okay, and there is some subspecial class of primitive words called Lindon words, and it is useful for text compression. Okay, so here is a picture of Masami Ito sensei, and picture of Pari Domoshi, Pari sensei, and they recently published their monograph titled Context-Free Languages and Primitive Words. And this monograph contains numerous results about primitive words and context-free languages. Okay. So here I want to introduce one more guy, who is Shirado Fazekas sensei from Akita University. His supervisor was Pari Domoshi at the University of Debrecen, Hungary. And he also studied with Ito sensei, Masami Ito, as a postdoc researcher in Kyoto Sangyo University. And because I moved to Akita University almost 3 years ago, since then I sometimes discuss with Shirado-san about combinatorics on words and primitive words. So gradually I have been interested in this conjecture. It sounds nice, it's very simple, but yes, of course, the simple conjecture like this is sometimes very difficult to solve, but it is free to feel interest, okay? So after studying several known properties of primitive words, I got some intuition like this. Of course, this is just an intuition. It's not a formal statement. So later I will give a formal statement of these two intuitions. The first one is that the set of primitive words Q is very large, but there is no good approximation by regular languages. We cannot have any good approximation for primitive words. And the second intuition is that in the case of context-free languages, there is no such language. I mean, every very large context-free language has some good approximation by regular languages. Okay. So this is my naive idea. It's turned to be false. Anyway, so my naive idea was that if we can formalize these two intuitions and prove it, then the conjecture is true. Okay. But actually, I proved that fortunately, intuition one is true, but unfortunately, the second intuition is false. So I will explain later those formal definitions and the proof. Okay. So anyway, to formalize this intuition, we should define what very large exactly means and what is approximation. And actually, defining approximation notion is very, very non-trivial, and there are several choices. So in history, there are several different models of approximation are proposed and studied. Last set approximation, minimal cover, convergent reliability, and bounded epsilon approximation, degree of approximation. And our model of approximation is rather close to Eisman and Lavigman's bounded epsilon approximation. But our model of approximation is strongly strongly inspired by Bach's measure density, which is a very classical notion back to 1946. Okay. So let me explain what measure density is, and then I will extend this notion to formal languages. So first, Bach considered a very basic infinite set of natural numbers, an underlying set of an arithmetic progression, S. So here, C can be 0. In this case, the S consists of only element D, singleton set. And then Bach defined its natural density, delta S, as like this. So C is 0 means S consists of just one element. It is finite, so very small, so whose density is 0, okay? And if C is not 0, there are infinitely many members of S with period C, so its natural density is defined as 1 over C, okay? So this value intuitively means the probability that the randomly chosen natural number n is in that set S, okay? Very intuitive. And then Bach extend this notion by using outer measure. So here, for a set of numbers S, not necessary to be an arithmetic progression, but arbitrary, its outer measure, denoted by mu star S, is defined as here. So let's take infimum of the summation of the natural density of arithmetic progressions that satisfy this condition. They are disjoint with each other, and their union is a superset of S, okay? And then if a set S satisfies the following condition, I mean the sum of its outer measure density and the the sum of outer measure of itself and the outer measure of its complement. So here S bar denotes the complement of S, equals to 1, okay? Then Bach said that if S satisfies this condition, then S is measurable. And this is a notion of measure density, okay? So technically speaking, the class d mu of all subsets of natural numbers satisfying this condition is exactly the Collat-Theodori extension of this domain D0. D0 consists of all disjoint finite, all finite disjoint union of arithmetic progressions, okay? And then Bach actually showed that several properties about this d mu, and as a basic result, he showed that this extension is proper. So now here I want to describe some observation from a formal language theoretic viewpoint. Because this domain D0 can be seen as the class of regular languages over a unary alphabet. Here, unary alphabet means the alphabet consists of only one letter A. So because we can see D0 as the class of regular languages because this equation holds. Actually, there is a bijection from them, between them. Because the set of lengths of words in a regular language L over a unary alphabet is a finite union of arithmetic progressions. This is due to Parik's theorem. Okay, every Parik image of regular language is semi-linear set, but here we only have one letter, so one-dimensional semi-linear set is just an ultimately periodic set, and which is a finite union of arithmetic progressions. So if we can define a density notion on the class of regular languages over an arbitrary alphabet, then we can naturally extend the Bach's measure density to formal languages by considering regular languages as a basic sets instead of arithmetic progressions, okay? So let me introduce density notion for languages. So here we list two density notions. The first one called the asymptotic density of L, defined here. So let's forget about this limit, just see this fraction. So the value of this fraction represents exactly the probability that a randomly chosen word of length n is in L, okay? And then the asymptotic density take its limit of probability. And then the density, sometimes called the average density, take average of probability, okay? So the basic fact asserts that if this asymptotic density converges to some real number alpha, then the latter density also converges to same number alpha, okay? But the converse is not true in general. So here we have a trivial counterexample, the set of all words of even length. So because the set of all words of even length have this property, because the fraction value of fraction is 0, 1, 0, 1, 0, 1, 0, 1, and never to converge. But its average is always half size, okay? 1/2. So it converges to 1/2. Okay, and this density has some very nice property for regular languages. So here we introduce two pretty facts. And the first one is that every regular language L has density, and it is always rational number. Okay, and the second pretty fact is that another characterization of non-null language, non-null regular language. Here, language is called null if its density is 0. And this factor 2 states that regular language L is not null if and only if L is dense. In this sense, L is dense means that it's intersect with the ideal language generated by any word W. Okay. So basically, not null means represents some largeness, some major theoretic largeness, and the dense represents some topological largeness. And this factor says that these two different definitions of largeness coincide in the regular case. Okay, so we want to note that not null implies dense is true for general languages, but the converse direction is not true for beyond regular languages. Okay. So I want to explain this fact further. So this direction is always true because we can show that by using well-known classical infinite monkey theorem. It states that stating that every ideal language is of density 1. Okay, and this theorem is sometimes called the infinite monkey theorem because the infinite monkey theorem states that for any given word W, such as the complete works of Shakespeare's play, which is a very long word, but a monkey hitting keys at random on our typewriter keyboard for an infinite amount of time will almost surely type the given word as a subword with probability 1. Okay. So now L is not dense means there is some word W such that which does not, whose ideal language does not intersect with L, okay, by definition. But so we have, because the complement of L contains this language A star W A star, the density, natural density of L satisfies this inequality. But by using infinite monkey theorem, we can say that this value is 0. So L is null, okay? So not dense implies null. So this red underlined part is true for general language. But the opposite direction is not true. Here is a very basic counterexample called the semi-Dike language, which consists of all consistent sequence of left and right parent. This language is dense because for any broken sequence of parents, we can add left parent from left, and we can add a suitable number of right parent and then make it consistent, right? So this language D is dense actually, but it is null. Density is 0. We can formally prove that this fact by using the connection between the number of semi-Dike words and the Catalan numbers. Okay. So anyway, we have introduced the two density notion, and especially this density have some good property. All regular language have density. So let's extend it by using Karateodo extension. For a language L, we define its outer measure as like this, okay? Infimum of the density of regular language R, which covers L. And we say that L is regular measurable if this condition holds. So L is regular measurable means exactly that its outer measure coincides with its inner measure defined here, the dual notion of outer measure, from inf to sup, from subset to superset, okay? So intuitively, L is regular measurable means we can take both upper approximation and both lower approximation with arbitrarily high precision, okay? So let's see examples of regular measurable context-free languages. So again, the example is semi-Dike language. So here we use letter A and B instead of left parent, right parent for readability. And the theorem states that this language D is measurable. Okay, so we notice that D have no best approximation by regular languages, because by factor 2, there does not exist a null regular superset of D, while D is null. But this theorem states that we can take arbitrarily precise upper approximation of D, okay? So let's see it. So define the language LK as this form. So here W bar A represents the number of occurrences of A in W, okay? So LK consists of all words of over A and B with the same number of occurrences of A and B modulo K. This is surely regular language. It can be defined by, accepted by K-state deterministic finite automaton, right? Okay. And this language gives a very rough upper approximation of D, but not very rough, because we can formally prove that the density of LK is 1 over K, which tends to 0 if K tends to infinity, okay? So because D itself is null, the empty set is always a best lower approximation of D, So the infinite sequence of pairs of this regular languages converges to D. Sorry. Okay, very simple. And here we list more complex examples, which I proved that all these languages are regular measurable, actually. So the first one and the second one is investigated by Flageolet. And he showed that these two languages, O3 and O4, are inherently ambiguous context-free languages, which means that there is no unambiguous context-free grammar generated. Okay, and the set of all palindromes is also regular measurable. The proof requires different idea with like languages, but yes, it is actually regular measurable. And the fourth language, G, sometimes called the Goldstein language, is also regular measurable. And this has some special property that the generating function of Goldstein language is non-algebraic. So it is also inherently ambiguous language by classical Chomsky system-Bezier theorem. And somewhat surprisingly, I showed that the language defined by Kemp is also regular measurable. Here, K is defined like this. The definition is a bit complicated, so maybe you don't need to read it. But the special property of this language K is that its density is non-algebraic. Okay. So in this sense, the language Z and especially K are very complex from a combinatorial viewpoint, but it is actually easy to approximate. Okay. So I actually showed that somewhat general result. I mean, so here is a theorem. For every alphabet A and every language L over A, we say its suffix extension as the language defined here, L prime. The concatenate with L with C from right, and then concatenate A cap C green star. Okay. This is the suffix extension of L by C. And actually, we showed that for any language L, this is regular measurable. And so because the language defined by Kemp is of this form, S1 cup ST, CA star is regular measurable because it is the suffix extension of S1 cup S2. Since S1 and S2 does not contain letter C, which only consists of A and B, okay? So this theorem tells us that the fact that there exists uncountably many regular measurable languages, like the situation is like that there exist uncountably many real numbers, which each real number can be represented as a convergent sequence of rational numbers, okay? So in this sense, we can say that regular measurability is quite relaxed condition. Very, very many languages have these properties. So let's turn to regular immeasurable languages, non-measurable languages, okay? So before that, we define some notion. For a language L, the difference of its outer measure and its lower measure, we say that this value is the regular gap of L. And then this value represents how a given language is hard to approximate. So L is regular measurable if and only if the regular gap is 0, okay? And if the regular gap is 1 for some language L, which means that L is very hard to approximate. So my previous intuition can be now formalized as follows. Q is very large means Q is null, density 1, but whose lower measure is 0. There is no lower regular approximation. And the second intuition can be formalized as follows. Every null context-free language satisfies with positive lower measure. So the gap of L is at most 1 minus epsilon for some positive real number epsilon. Okay, and fortunately, intuition 1 is true because we can formally prove that Q is null, but every regular subset of Q is null. So in particular, every non-regular language contains infinitely many primitive, non-primitive words, I mean. And the proof of Theorem 1 is very easy and maybe folklore because the structure of generating function of Q is well studied, but I can't find any literature which explicitly pointed out this fact. And the proof of Theorem 2 uses some basic semi-group theory. So I omit the proof, but if you're interested in the proof, see my paper, please. And then the second intuition. This is actually false, wrong, because we construct a counter example, M2 bar, which is null, but whose lower measure is 0. And it is actually deterministic context free. So I proved this theorem and we got this result as a corollary. And here, the language M2 is defined like this. The words with this property asserting that the number of A's are strictly larger than twice of the number of B's. This language is null, but whose outer measure is 1. Okay, so I mean regular gap is 1. Because we can construct a deterministic pushdown automaton recognizing this language, this is a deterministic context free, so its complement is deterministic context free too. Okay, so this counter example is very inspired by result of Eisman and Rabikmar's 2011 paper, and they showed that in their setting, the majority language is hard to approximate. Okay, and actually their proof, no. So actually I simplified and generalized their proof and obtained this theorem. Okay, the proof is not very complicated, so I will demonstrate how to prove it. So it is some basic algebraic theory of regular languages, but it's not difficult, I think. Okay, so first, M2 is null. M2 is null, I mean the M2 is of density 0, can be shown by using just applies the law of large numbers, because this condition is strictly greater than the twice of number of B's is very far from the average, because the average number of the occurrence of A is always n over 2. Okay. So now next we show that this part whose outer measure density, whose outer measure is 1. So let L be a regular language with this property, not null, okay? And then we show that this never to be a superset of M2, and this is equivalent to the complement of L intersect with M2. Okay. So let eta be the syntactic morphism of the complement of L, because this is a regular language, then the M is finite by Myhill-Nerod's theorem. Now we define C as the maximum of the minimum of the length of W. And here, this is a very defined natural number because M is finite, we can take its maximum, okay? And it is always natural number. And then consider about the world, the consists of only A for C plus 1 repetition of A, okay? So from this assumption, L satisfies these properties, the complement of L is non-null. So by using infinite monkey theorem, we can say that L is the complement of L is dense. Okay. So this means that there is pair of words x, y, such that x, a for C plus 1, y is in the complement of L. And also we can take such x and y with length smaller than C because of this definition of C, okay? So now let's count the number of B's in this word. So the central part consists of only A's. So the number of B's less than to the sum of the lengths of X and Y, which is less than 2C, okay? And this is strictly smaller than the half of the number of A's because this central part contains too many A's, okay? So this is in M2, so M2 is not a subset of L, okay? And consequently, the outer measure of M2 is 1. So this is the proof, okay? Not very complicated. Anyway, so from this theorem, we have this corollary, which is a counterexample of my original intuition too. So here is a summary of regular measurable languages and some example of regular immeasurable languages. So by definition, all bounded language of this form is a regular measurable because by definition, this language is a regular and it gives a good approximation from above, and it is null. Okay. And so in this talk, we introduced the language M2 bar, which is actually a DCFL, deterministic context free, but has some complex properties as like the set of primitive words. Density 1, but the inner measure is 0. Okay. So now I want to conclude my talk with few open problems. So the first one is a rather fundamental one. I'm interested in whether we can give an alternative characterization of the class of null context-free languages and null context-free languages, respectively. So I think this kind of fundamental study is required to attack problems like the primitive words conjecture, because the set of primitive words is con-null, okay? Sorry. So here we note that there is no hope to have a decidable characterization because it is undecidable whether a given CFG generates null context-free language or not, okay? This is shown by very recently by Nakamura in his PhD thesis, okay? And the second problem is also a fundamental one. So can we give an alternative characterization of regular measurable languages, in particular regular measurable context-free languages? So I think there could be many types of different characterization because, for example, in measure theory, Lebesgue measurable sets or Jordan measurable sets have several different but equivalent conditions. And I also note that there is also no hope to have a decidable characterization because the regular measurability is closed on the left and right quotients. So by using Greiber-Haas meta theorem for undecidability, we can say that the regular measurability for context-free languages is undecidable. Okay. And the third one is application. I'm interested in whether we can find a language class that separates the primitive words and all CFLs in this sense. Okay, here we note that the notion of measurability can be parameterized by a language class C, not necessarily to be the class of regular languages. So we can, by using same manner, we can define its C outer measure and C measurability for languages, okay? And separates means that the situation. Q has full C gap, but no null context-free language has full C gap. Or more simply, Q is C immeasurable, but every null context-free language is C measurable. And I actually conjecture that Q is CFL immeasurable. Okay, but by definition, every context-free language is CFL measurable by definition. But because the structure of context-free languages is very complex, there is no good theory about the generating function of context-free languages. So I think it is better to consider DCFL or unambiguous CFLs as a first step. And I also interested in the unCA measurability. Here, unCA stands for unambiguous constraint automata languages. あと5分ぐらいかな。Okay, I think I have 5 minutes more, so I want to briefly discuss about constraint automaton regression. Okay, so a constraint automaton is a pair of a finite automaton, usual finite automaton, and a semilinear set S, or Pressburger definable set S, whose dimension is exactly the number of transition rules of automaton A. And the acceptance condition is defined here. The constraint automaton A and S accepts a word W if and only if there exists an accepting law labeled by W. So this condition is equivalent to the usual acceptance condition of automaton. But in the setting of constraint automata, there is further constraint. I mean, the vector N1, N2, Nd is in S further. But here, Ni represents the number of occurrences of the ice transition rule in law. Okay, so here we implicitly assume that the transition rules are totally ordered. Okay. So let's see very simple example. Simple automaton consists of only one state and only single loop. So if we regard this automaton as a usual automaton, then it accepts all words over A, B, and C, trivial automaton. But if we define the semilinear set S as like this, so the diagonal in the cube of natural numbers, then it accepts exactly the language called mix, which is a non-context-free language, consists of all words of the same occurrences of A, B, and C. Okay. So, okay, further we say that constrained automaton is unambiguous if the underlying automaton A is unambiguous. And the class of unambiguous constraint automata is a very, very, very well-behaved class. So here ANCA stands for the class of all unambiguous constrained automata recognizable languages. And this language class contains many, many counting type languages, including mix, O3, O4, M, and M2 bar. And ANCA language has very good structural property, which recently shown by Boston et al. In their ICALP paper. ANCA language has a holonomic generating function. A holonomic generating function is some kind of generalization of algebraic generating function. And ANCA, the class ANCA has very, very rich closure properties and very good decidable property. So surprisingly, the regularity is decidable for this class. So regularity asks whether a given unambiguous constraint automaton recognize a regular language or not. And this kind of property is undecidable for some language classes with some good closure property and undecidable universality problem. It is exactly the Greiber-Hazmeta theorem. But for the class of ANCA, it is decidable. And still, context freeness is decidable for some subclass of ANCA. And this is my result. And this year's DLT's paper, I showed this property holds for some subclass of ANCA. Okay. So, okay, this is a summary of open problems. And okay, I'm satisfied. That's all. ありがとうございました. Thank you.
Thank you, Ryoma. So I'm gonna unmute all of you so we can clap. So you're all unmuted now. So thank the speaker. Let's thank the speaker.
Okay.
Right. So if you have any questions, you can either raise your hand or you can please raise your hand using that feature. So I can let you ask a question. Are there any questions? There you go. So Peter has a question.
Yes, thanks. This notion of a constrained regular language, there you are counting the transitions. Do you get an equivalent notion if you count the numbers of time you are passing a particular state? Or is that a different class?
Mm-hmm.
Sorry, I'm muted. Okay, so actually I cannot understand your question. Sorry, please.
You are counting transitions.
But constrained automaton?
In the constrained automaton, you are counting the number of times a particular transition has been made during a run. But if I look at the sequence of intermediate states, you can also count the number of times you reach a state.
Yes.
And would that lead to an equivalent concept of constrained languages?
Yes, if we count the instead of transition rules, if we count the number of past times of states, I think we can construct the same from constrained automaton we can construct an automaton that recognizes the same language in your setting. So yes. we can modify the definition of constraint
I
automata.
don't see immediately how to do it, but it sounds quite plausible that the two notions would be equivalent.
It's
except
actually
for maybe
equivalent
some...
because for each transition rules, we can introduce the states which corresponds to this transition, and then, yes, we can modify.
There may be some trivial obstructions for very incidental languages, because you always have to end with an accepting state. So that should be encoded in the similar linear set in some way. Okay, thanks.
Any other questions? Please feel free. I have a rather naive question. In the kind of earlier part of the talk, you mentioned that there are several notions of models of approximations, and
Yes.
you're using something close to one of them. So I'm just wondering if you could try, I don't know, another notion and do this kind of reasoning. Is that possible or feasible or interesting?
Of course, maybe possible, because there are several choices. So in this model of approximation, we adopt backwards strategy, backwards measure density, and we use the density notion here. But there are several different types of density notion is also investigated in algebraic coding theory. So, but my opinion is that this density notion is, in some sense, most natural one. So I think, yes, there is some possibilities, but I'm mainly interested in this setting. Yes.
Okay. Yeah, I was wondering because I don't know, but there might be some possibility that if you use a different notion of approximations and you get different cut of measurability to characterize CFLs and Qs. But yeah, but I understand it's something natural or like useful.
Yeah, maybe by using another density notion or different approximation model, maybe this figure will be changed.
Might change.
Maybe, yeah.
Yeah, just one. Okay, there's another question. So, so David has a question. I'm unmuting you.
Yeah, thanks. I mean, so my question is kind of similar to the previous one, really. So, to me, another very natural way of defining density would be something a bit closer to like sort of L1 distance. How does that relate to your model?
David-san, sorry, could you speak more slowly?
Sorry. My question is similar to the previous question. Okay. So to me, it would seem natural to define something more like sort of L1 distance from regular language.
Distance.
That or something. How does that relate to your model? Do you know what that might give you?
I'm not aware of L1 distance. What is this? What's L1 distance?
Oh, well, I just mean, you could say for a given regular language, how many words does it disagree with your real language, and then add them up weighted in some way, because you should count longer words less strongly somehow. And then you could ask, can you get that as close to 0 as you want, for example, rather than saying you need a regular language which contains all of your language or is completely contained in your language. You could allow some differences.
Okay, I understand your question. Okay, so maybe it is the concepts like you stated is maybe sometimes called degree of approximation, or yes, there is another approximation model which is not necessary to completely cover that language, but maybe some the exception is allowed. And this is exactly the concept that's called, okay, Eisman and Ravi-Kumar introduced the 3 types of approximation: bottom approximation and top approximation, and the mixed approximation. And mixed approximation sounds exactly what you said, but I think okay, in major theoretic viewpoint, one should completely cover the given set. So in major theoretic viewpoint, such kind of mixed approximation does not allow. I'm not sure, but maybe there is some possibility, and maybe interesting.
All right, so I think it's good time to thank the speaker again and move on to the coffee break / discussion session. So I'm unmuting you all. Yep. So let's thank the speaker again. So now I stop recording.